my last lecture on synthesis of amino acids, I had discussed in detail the methods of preparation of amino acids. That is, amino acids can be prepared by reductive amination of alpha keto acids. They can also be prepared by amination of halo acids. Then we discussed in detail the Strecker synthesis, method of synthesis of amino acid, as well as Gabriel's malonic ester synthesis. This was followed by discussion on physical properties of amino acids, and we discussed that the solubility of amino acids in water is variable. That is, it depends on the nature of the side chain which is present in a particular amino acid, along with the carboxylic and the amino group, which is the characteristic groups of the amino acid. So it will depend whether the side chain is non-polar, polar, acidic or basic. The next property that we discussed was that the dipole moment of amino acids is greater than that of amines as well as carboxylic acid, and we also found that the melting point of amino acids is high. That is, if we talk of the simplest amino acid, which is glycine, it starts decomposing at 200 degrees Celsius and melts at 260. Why is this the behavior? That is, why is the melting point higher than that of corresponding amines or carboxylic acid? It is because we know that amino acids exist as dipolar ions. Now, continuing from here, in today's lecture, I shall be discussing in detail the zwitterion formation, the isoelectric point, and then the acid and basic properties of amino acids along with their titration curves. So, when I talk of the structure of an amino acid, so can we look at the structure which is coming on the screen? That is, what is the structure of the amino acid? So, what we find is that the structure is, the basic structure of amino acid is that it has a NH2 group, it has a CH2 group, and it has a COOH group. So, when we talk of this, what we find is that when we talk of the group, that is the NH2 group and the COOH group, so do you think this is the correct structure which will represent all the properties that we have discussed? Then the answer is no. This structure is rather simplified structure, but it is incorrect, because in it we are showing that the amino group is present as NH2 and the carboxylic group is present as COOH, whereas this is not the case. So, when we say that amino acid is existing as a dipolar ion or a zwitterion, what we mean here is that in an amino group, in an amino acid, NH2 is the basic group and COOH is the acidic group. So, what happens is that internal acid-base reaction takes place, as a result of which the amino group is protonated into an ammonium ion and a carboxylic group loses its proton to form a carboxylate ion. So, as a result of this, what we get here is a zwitterion. So, what we say now is that amino acids are acidic in nature, are ionic in nature, and when they are ionic in nature, you have to remember that the structure will depend on the pH of the medium, which I shall be discussing in detail. And then what we know is that, as I have already said, that in an amino acid, a COOH group will lose a proton, giving a carboxylate ion, and our amino group will be protonated to give us an ammonium ion, resulting in the formation of a zwitterion. Now, zwitterion is derived from a German word which means zwei. Zwei means double, or we can also say that zwitterion means that it is an hybrid ion. So, if I say it is an hybrid ion, here I have shown the structure of amino acid here, and then what we have shown is the zwitterion. So what has happened here, that H plus from here, that is of the carboxylic acid, has gone and reacted with the lone pair of electrons on the amino group, resulting in the formation of a zwitterion. So what we observe in zwitterion is that amino group has a +1 charge on it, whereas the carboxylate group has a -1 charge on it. And if we add the two, the net result is 0. So that means zwitterion is electrically neutral. So what we find is, in the major existence or the major representation of an amino acid is by zwitterion and not by the uncharged structure of the amino acid, which is this. Now let us look into the next property, that since amino acids have both the COH group and the NH2 group, as a result of which a zwitterion is being formed. And then what we find is that in zwitterion we have a COO minus group which will act as a base, and an NH3 group which will act as an acid. So what you have to remember is, in amino acid, it is not the COOH group which is acting as an acid and an NH2 group which is acting as a basic group. It is the other way around, that is COO minus, that is the carboxylate group, is acting as a basic group, and NH3 positive is acting as an acidic group. So what we find here is, we can now explain that amino acids are less acidic than the corresponding carboxylic acids, because in them the acidic group is NH3, whereas, and they are less basic than the amines, because in them the basic group is COO minus. So when we dissolve amino acid in an aqueous medium, what happens is that in an aqueous basic medium, the OH minus will pick up a proton from the ammonium ion, resulting in the formation of a conjugate base. And whereas when we do the reaction in an acidic medium, then what we find is that the carboxylate group here is acting here as a base. It will take up a proton from water and will be converted into its conjugate acid. Hence we say that amino acids are ampholytic in nature. So now when we talk of it, now carrying out further the discussion, what we've seen is what will be the predominant form of an amino acid. The predominant form of an amino acid will depend on the pH of the solution. So what we know is that if the pH is too low, it is the acidic, in the acidic solution, it is the carboxylate group which will be protonated to a COOH group, because it is this group which is short of proton. It is acting here as a base, so it will pick up a proton from the surroundings, and this will have a positive charge on it. So what you have to remember is that when we are carrying out the reaction, or the reaction medium is acidic in nature, then the amino acid will have a net positive charge on it. So, and now as we raise the pH gradually, what we'll find is, that is, if we are starting from an acidic medium, both the groups, that is COO minus, will be protonated, as well as ammonia will, the amino group will also be protonated to give us an ammonium ion. So the entire group is amino acid has a positive charge on it. Now as we raise the pH of the medium, that is, we are decreasing the hydrogen ion concentration, then what we find is that the COOH group will lose its proton and will be converted into a zwitterion. And when the pH is raised further, then what we find is that the ammonium group will also lose its proton, and the molecule as a whole will now have a negative charge. This I have demonstrated with the help of a slide here. with the help diagrammatically here. So when we look at the diagram, so let us see, we are starting with an highly acidic medium, that is the low pH. So when we talk of a low pH, what you have to remember is that the concentration of protons in the vicinity is high. Since the concentration of the protons in the vicinity in the surroundings is high, and we know that amino acid is acting as a zwitterion, the only negative charge is present on the carboxylate ion. So this carboxylate ion will pick up the proton from the surrounding and will become positively charged. So what we find is that at low pH, amino acid will exist as in its cationic form. Now we slowly raise the pH, and when we slowly raise the pH, that means the hydrogen ion concentration is going down, the OH ion concentration is going up. So in that case, the carboxylic group will undergo deprotonation to give us a carboxylate group. At this point, what we find is that is the charge is equal, that is ammonium group has +1 charge, carboxylate group has -1 charge, so the net charge is 0, and at this point the amino acid will occur as a zwitterion. Now we will increase the pH further. Then what we find is that it is only the ammonium group which is positively charged. It will lose its proton, and we will get a species in which a carboxylate group has a negative charge. So that means this is an anionic form. So this is how the pH will affect the existence of amino acid in a solution. So now we come to the next point. What is the isoelectric point? Isoelectric point is derived from the word iso, which means the same, and the electric is drawn from the word charge. So isoelectric means that the molecule is having same charges. Now what I mean by saying same charges is that it is having equal charges. That is, it will have if it is having positive charge, it will have one positive and it will have one negative. So this is what we've shown here, that in this case, ammonium group has +1 charge and the carboxylate group has -1 charge. They cancel out each other and the net charge is 0. So isoelectric point is that pH at which the amino acid will exist as a zwitterion. So when we talk of existence of amino acid as a zwitterion, what you have to remember is that when it is existing as a zwitterion, its solubility in a particular buffer or a solution will be minimum, and since it is existing as a zwitterion, that is the positive charge and the negative charge is equal, and since the positive charge and the negative charge is equal, it will not migrate, and if we pass electricity through this solution, it will not migrate towards either of the electrodes. It will not migrate towards cathode and it will not migrate towards anode. Here again what I have shown here is that is at low pH, amino acid will exist as a cation. At a neutral pH, which in case of amino acids is less than 7 because it depends on the nature of the side chain, then that is the isoelectric point of the amino acid and it will exist as a zwitterion. Whereas if we increase the pH further, then what we find is that it will exist as a anion. So now what we find is, again the same thing, I am repeating this again and again because we will be using this concept while we discuss that titration curves of amino acid. So now we know that at low pH the concentration of proton is high. Since the concentration of proton is high, therefore both the amino group and the carboxylate group will be protonated and they will exist as NH3 and COOH groups respectively. At a very high pH, deprotonation will take place. Therefore, both amines and carboxylic acid will be deprotonated. So the amines in amino group will exist in its NH2 form, and the carboxylic acid will exist as carboxylate, that is COO minus group. At neutral pH, amines will be protonated and carboxylates will be deprotonated. So at this point, amino acid will exist as a zwitterion. So now I've got a question for you here. Now I have glycine molecule with me, and glycine is the simplest amino acid. So what we find is, you have to remember the basic structure of an amino acid. That is, when we look into the basic structure of an amino acid, what we find is that a alpha carbon is attached to a COH group, and it is then attached to a NH2 group. Then it has an H, which is the basic structure of an amino acid. The second H is variable, that is, we can have any other group in it. For example, we can have a phenyl group in it, then it will become phenyl glycine, or we can have a CH3 group in it, when it will become a alanine. And if we have acidic groups here, it will become an acidic amino groups and acidic amino acid. And if we have a basic group in the side chain, then the amino acid will be basic in nature. Now the question that has been asked is, what will be the structure of an amino acid, that is glycine, at pH 1, 7 and 12? So what you have to remember here is, that is when we are talking of the low pH. At low pH now we have to remember that both the amino group as well as the carboxylate group will be protonated, since the concentration of H ions is high. So in this case it will exist in its cationic form. Now if we go on to the next structure, then at neutral pH, what will happen? That is, the COOH group will be deprotonated. When COOH group will be deprotonated, we will get a zwitterion. That means at neutral pH, which for amino acids is, I think, between 5.6 to 6 depending on the side chain, they will exist as, for non-polar amino acids, sorry, not for all, they will exist as zwitterions. Now if we increase the concentration of the OH ions further, then what we know is that in this case the ammonium ion will also undergo deprotonation and it will be converted into NH2 group. So in this case now the amino acid ion will have a negative charge on the COO group. So now it will exist in its anionic form. So this is again what I've shown here is the three forms of amino acids, and we say that in spite of amino acids having both the groups, the amino group as well as the COOH group in the molecule, they will act as different entities, that is, their properties will be different. Now let us extend this knowledge and use it to find out the acidic and basic properties of amino acids. So now we know that if we take in an aqueous solution, we talk of an amino acid, we know that amino acid will exist as a zwitterion, that is, it will have a weakly acidic alpha carboxylic group and it will have a weakly basic alpha amino group. Not only this, what we find is that in some amino acids, the side chain may be acidic or a basic group. That is, if I talk of an acidic amino acid, then an additional acidic group will be present on the side chain, whereas if I talk of a basic amino acid, basic group will be present there, and these groups will be ionizable groups. So what we find is that along with the COOH group and the COOH group and the amino group, there will be another ionizable group which is present in the side chain, which will affect the properties of the amino acid. So if another COH group is present in the side chain, as in aspartic acid and glutamic acid, then the amino acid will be acidic in nature. And if a basic group is present in the side chain, then that particular amino acid will be basic in nature. Next, what we find is, now we know that if we talk of a peptide chain, then on one side we will have a free amino group which we call as the N-terminal, and on the other side we will have a COOH group which we call as a C-terminal. So we will be having two free groups, and along with that we may also have certain side chains. So these side chains along with these groups will act as buffers. How will they act as buffers? This we will be discussing shortly. Now we know that we know that amino acids are weak acids. So when we talk of a weak acid and its conjugate base, the concentration of the acid and its conjugate base can be found out by Henderson's Hasselbalch equation. So what does Henderson equation say? It says in order to determine the nature of a molecular and ionic species that are present in aqueous solution at different pH, we will use this equation. And what we find from this equation is that when the value of pH of the solution, when the solution of the pH is equal to the pKa value, that is pK is nothing but the dissociation constant of an acid, that is when acid will ionize to give us H plus in the solution, then the concentration of the HA and that is the concentration of an acid and its conjugate base will be 0. So now, to make this concept simple for amino acids, what you have to remember is that, and this is the general concept also, that is when the pH is below the pKa, that is when the pH is less than pKa, then what we have to remember is that all the N groups or the side chains will be protonated. That is, amino acid will exist in its cationic form. And when the pH is above the pKa value, that is when the pH is more than the dissociation constant, then all the side chains will be deprotonated and the amino acid will exist as an anion. And when the pH is greater than that means when pH is greater than pKa, what will happen? Deprotonation will take place. And then what you have to remember is that when pH is equal to pKa, then we have equal amount of an acid, weak acid, as well as its conjugate base. Then in that region, the amino acid will act as a buffer, that it will have show its buffering capacities. So this is what I have again elaborated here. Again I have shown the same thing, that is as we keep on increasing the pH, the amino acid will undergo deprotonation to form a zwitterion and then it will be converted into its anionic form. So now if we talk of the general reactions of acid and bases, acid and basic properties of amino acids, and we consider that general titration curve of an amino acid. So what you have to remember is that when you are plotting a graph, the graph will be plotted between the pH and the amount of base that we are adding. pH will be taken on the y-axis and the base will be taken on the x-axis. So what we know is that in acidic medium, you have to remember that amino acid will exist in its protonated form, and then as we slowly increase the pH of the medium, that is when the hydrogen ion concentration is being decreased, we will get 3 plateaus on the graph. Now what is the significance of the 3 plateaus, the 3 positions that I have shown, that is 1, 2 and 3. Now 1 is the dissociation constant of the acid. That is, this is a point where half of the original acidic amino acid will be titrated and will be converted into zwitterion. This we will represent by 0.1, or in the titrations we will be represented it by pK1. Then we talk of the 0.2. 0.2 is the point at where the amino acid will exist truly in its zwitterion form. And then when we go to 0.3, what we find is that here the zwitterion, there is half of zwitterion and half of the amino acid is present in its basic form. So this general titration curve we will be using now to discuss the titration curves of different amino acids. And what we found was that in general titration curve we had 3 points: point number 1, point number 2 and point number 3. What is the significance of these points? So what we find is that point 1 will represent that point. It is the pK1 value, where at which point there will be equal amount of the acidic form of amino acid as well as zwitterion. At point 2, the amino acid will exist entirely as zwitterion, and this point is known as the isoelectric points. And the point 3 is representing the point where there is equilibrium between the zwitterion and the anionic form of the basic form of the amino acid. Now let us discuss this example by taking the example of simple titration curves of simple amino acids. So when I talk of a simple amino acid, then in that case it does not have a dissociable R group. Now since it does not have a dissociable R group, we will find that the titration curve will be similar to the one which I have to the general titration curve. That is, it will have only 2 plateaus, which will correspond to the dissociation and titration of the alpha carboxylic group, and it will have pK2, which will correspond to the dissociation of the ammonium group. So what we find here is, that is, if we talk of the solution, now let me look into this. So what I have done here is, I have shown you 3 forms of glycine, glycine, and what we've seen here is, that is, if I talk of glycine, then the first, at low temperature, at low pH, which is the 0 pH, in that form both the groups, that is the amino group as well as the carboxylic group, is protonated. And now why is it protonated? Because the hydrogen ion concentration is high in the medium. Now as we increase the pH of the medium, what we find is that we will get a pK1. So what is happening here is that this carboxylic group, this being more acidic than the ammonium group, it will deionize, it will undergo deprotonation. So what you have to remember here is that when we are starting with this species is diprotic in nature. That is, it can give 2 protons. 1 proton it can give from the COOH group, and the second proton it can give from the NH3 group. So when we increase the basicity, or when we increase the concentration of OH ions, what we find is that these OH ions will bring about the deprotonation of this carboxylic group, and it will be converted into a second species. Now if we look into this species, what we find is, in this particular species, the positive charge on ammonium group is cancelling out the negative charge on the carboxylate group, as a result of which we get a neutral ion, that is, we are getting a dipolar ion, or we are getting a zwitterion. Now as we increase the pH further, the H ion concentration will decrease further. That is, the OH ion concentration will increase. And now the only alternative is that this ammonium group has a proton which it can lose. So the deprotonation of the ammonium group will take place and it will be converted into its anionic form. Now, if we look into the different forms, what we find is, if we look in the acidic medium, then the COOH group is not ionized. So that means it has no charge on it, whereas the ammonium group has +1 charge on it. So it is existing in its cationic form. As we increase the pH, and then what happens is it will undergo deprotonation at the carboxylic group. And the deprotonation will always take place first at the alpha carboxylic group. It will lose a proton and will be converted into a zwitterion. Next, it will again further undergo deprotonation, and in this case you have to remember the net charge is 0. Then when we do further deprotonation, what we find is that this amino group, ammonium group, will lose its proton further and will be converted into amino group. Now, amino group has no formal charge on it, whereas the carboxylate group has a negative charge on it. So this species will have a charge of -1. So now if I represent it in form of a titration, then this point, please remember, is the pK1, where there is dissociation of the carboxylic acid, and this point is the pK2, where there is deprotonation of the ammonium ion. So what we find is that when we start the reaction, the titration from an acidic medium, and we gradually decrease the concentration of H+ ions, then what happens is that this acid undergoes deprotonation. The carboxylic group starts undergoing deprotonation, and at this point, that is the pK1, which is 2.34, at this pK1 it will lose its proton, and since it will lose its proton, what we find is that there will be equilibrium, or there will be equal amount of the acidic amino acid as well as the form in which it has lost its proton. So at this point, what we find is at pK 2.3 there will be equal amounts of the unionized acid as well as the zwitterion, that is the acidic form of amino acid, and the zwitter form and the zwitterion. Now, as we slowly increase the pH of the medium, what we find is that at a particular pH, that is if we take the center point of this graph, of this part of the graph, what we find is that at a particular point of the pH, this amino acid will exist only in its zwitterion form. So when it is existing as a zwitterion, this pH will be equal to the pH of the pH of the amino acid will be equal to the pH of the buffer, and this is the isoelectric point of the titration, or the isoelectric point of the amino acid. Now we are increasing the pH further, then we find is that at another point, which is 9.4, the deprotonation of the ammonium group takes place. And when the deprotonation of the ammonium group takes place, then what we find is at the center point here, now there is equal concentration of the zwitter ion and this anionic form. So what has happened is that after becoming a zwitter ion, as we keep on increasing the pH, this ammonium group undergoes deprotonation, and if we increase the pH further, then what we find is at pH 13 only the anionic form of the glycine will be present. So that means we have only two plateaus or two influx points in this titration because we do not have a ionizable side chain in it. Now if we go back here, what we find is, now if you look from this region to this region, what we find is that as we are adding the base to it, there is not much change in the pH. So this region of glycine, that is, we talk of the pH value from 1.34 to 3.34, this can act as a buffer zone. So this is one buffer zone, and the second buffer zone will be this, in which again what we find is there is little change in the pH on adding base to the glycine, and this way will be, and the buffer zone will be between 8 to 10, between 8.4 to 10.4. So that this is the titration curve for a simple amino acid. Now let us go on to an amino acid which is having a, let's say, a acidic amino acid which is having a COOH side chain. So when I say it has a COOH side chain, what will happen here is, that is, we will have three points in it. But before I proceed further, I would like to discuss one question here, that is, which is normally asked in the exams, and the question which is asked is, what is the PI value of glycine? Then please remember, in that case the pKa values would be given to us. You don't have to remember the pKa values. So we know that we have two dissociation constants for this, pKa1 and pKa2. pKa1 is that dissociation constant for a COOH group, and pKa2 is the dissociation constant for the ammonium group. And as I've already shown you in the graph, that is, the pKa values are the, when we talk of the graph, what we find is that the PI value is the intermediate, it is halfway between the pKa1 value and the pKa2 value. That means when we have to calculate the PI value, what you have to simply do is, you have to add the two values, that is pK1 value and pK2 values, and then divided by 2. So what we find here is, so if we have to find out what is the isoelectric point of glycine, so we add the pKa1 value and we add the pKa2 value. So what we find is that the pKa1 value is 2.3 and the pKa2 value is 9.7. So if that is the case, you have to simplify it. For 2.3 we can take as 2, and for 9.7 we can take as 10. So if we add 10 and 2, the value will become 12, and then we divide it by 2, the value will become 6. Here I would like to point out a correction in what I've already, which I have explained to you earlier on, is I think I said that the pKa value for ammonium ion in glycine was 9.4. So please, I stand corrected, it is not 9.4, it is 9.7, and the buffering zone will be between 8.4 to 10.4. Now let us talk of a titration of an acidic amino acid. So if I talk of an acidic amino acid, we know we have two acidic amino acids. One is the glutamic acid and the second is the aspartic acid. So that means when I talk that they are acidic in nature, what I mean by saying they are acidic in nature, that is, along with the alpha amino group and a alpha carboxylic group, a second carboxylic group will be present in the titration. And when this is present there, what you have to remember in this case is that the titration curve will be different from that of glycine, or the titration curve will be different from a general titration curve, because it will have 3 pKa values. First pKa value will be for the carboxylic group. Second will be the pKr value, which will be for the dissociation constant for the side chain, and then we will have the pK2 value, which will be the dissociation constant for the ammonium group. So that means we will have 3 plateaus, and each one will correspond to a dissociation of a proton from the amino acid. So now we know is that the R group will occur between the pK1 and pK2. So that means now when we talk of the dissociation constant, that is pKr, it will always be between pK1 and pK2, and the second plateau, that is pKr, will correspond to the titration of this group. So now later on I will discuss, so what you have to remember from what we've already discussed is that now if we will find out, we have to find out what is the isoelectric point of this reaction, or what will be the zwitterion, at what point will this amino acid exist as zwitterion. This will be between pK1 and pKr. This I will be now explaining in detail with the help of the titration curve. So now if I look into this, so what we find here is that if I look into the structure of glutamic acid, so what we find is, if we are looking into the highly acidic medium, then you have to again remember that in highly acidic medium, all the groups will be protonated. That is, alpha amino group will be present in form of ammonium group. COO minus, that is the zwitterion, that is the alpha carboxylate group, will be undergo protonation, and it will be present as COOH group. And then we have a COOH group of the side chain, that is the acidic group of glutamic acid. So now what we find here is that when we look into the first structure, then in first structure what we find is that both the carboxylic groups, that is the alpha carboxylic group of the amino acid and the COOH carboxylic group, which is present in the side chain, are unionized, that is they have no charge on it. Only ammonium group, that is the amino group, is present in ammonium group in form of ammonium, so it has a charge of +1. So the net charge on this structure will be +1. That is, in highly acidic medium, amino acid will exist as a cation. Now what happens is, as we increase the pH of the medium, this ion will lose, this molecule or this identity will lose its proton. Now what you have to remember is, we have two groups, two carboxylic group. One is the alpha carboxylic group and other is the carboxylic group which is present in the side chain. What you have to remember is, and we also have a ammonium ion in it. So in between these three, you have to remember which will undergo deprotonation first. It will always be the alpha carboxylate group which will undergo decarboxylation first. So this pK1 is the dissociation constant of the alpha carboxylate group. It will lose its proton and will be converted into second form. Now when we look into the second structure, what we find here is that one of the carboxylate groups is unionized, whereas the alpha carboxylate group is present as a carboxylate ion and alpha amino group is present as a ammonium ion. So that means ammonium ion has a charge of +1 and the carboxylate group has a charge of -1. So these will cancel out each other and the net charge will be 0. That is, here the amino acid is existing as a zwitterion. Now what happens in the second phase, as we are increasing the OH ion concentration and decreasing the H plus ion concentration, you have to remember, as we are making the medium basic, the particular structure will undergo deprotonation. Now the question is, which group among these two will undergo deprotonation, whether it will be the alpha amino group or the carboxylic group. So this group will undergo deprotonation here. So when this undergoes deprotonation, we will get this species. Now, and this will be the pKr. Why is this known as the pKr? Because in this case, the deprotonation is of the carboxylic group, which is present in the side chain. So now what we have here is, this species has two negative charges on it, one on the carboxylate group, that is the alpha carboxylic group, and the second on the group which is present on the side chain. So that means the negative charge is -2 and it has a positive charge on the alpha amino group, which is present as an ammonium ion. So the net charge on this species is -1. Now as we increase the pH further, what we find is we have still one group left which can undergo deprotonation. So as we increase the pH of the medium, this ammonium group will also undergo deprotonation and will be converted into NH2 group. So now when we look into this structure, what we find is NH2 has no charge on it, whereas the two carboxylate groups each have a charge of -1. So that means this species will have a charge of -2. So now what we revise this is that at low pH it will exist, the glutamic acid will exist in its cationic form. At a pH between pK1 and pKr, it will exist as its zwitterion, as a neutral ion, and as we increase the pH, it will keep on losing its protons and ultimately it will be present in its anionic form. So let us look into the graph of this reaction. So what we find is, if we look into the graph of this reaction, we are having three plateaus in this. One is this, second is here, and the third is here. So what we find is that, as I've already said, I've explained this in detail, that is at acidic medium, glutamic acid is in its purely positively charged form, that is all the groups are protonated, and as we increase the temperature, the alpha carboxylic group will undergo deprotonation, which is pK1, which has a value of 2.19. And at this point, now you already know that there will be equal amount of the charged species and the neutral species. So we have a equal form here. Now as we keep on increasing the temperature, what we find is that this cationic form of the acid will keep on changing into its zwitterion till we reach a pH where the whole of this will be present as zwitterion. Now when we increase the pH further, what will happen is that the second carboxylic group, which is present in the side chain, will undergo deprotonation, that is the pKr, and that value is 4.25. And this, now again we will have a equal amount between the zwitterion and the second form. Now when we keep on increasing the pH further, gradually what we find is whole of this form will be changed into its anionic form at a pK2 value. So this is what we've shown here. So now the question that can be again asked from us is, what is the pKr of this, what is the pi of this acid? So what you have to remember is that when we are talking of an acid, it may be aspartic acid, it may be glutamic acid. The isoelectric point is going to be the average of pKi1 and pKr, because this is the structure which is sandwiched between the cationic form and the anionic form, and this is the species which has no charge on it, that is, it is electrically neutral because the positive charge is cancelling out the negative charge. So now if the question is asked that what is the pi of a glutamic acid, so what you have to remember is that you are going to take the average of pK1 and the pKr, that is, we are going to take an average of pK1, pKa1 and pKr here. So what we find is that we are going to take an average of 1.9 and the second value, that is 3.6, divided by 2, when we will get the pi value of 2.7. So this is how we will calculate the pi of an acidic amino acid. So for an acidic amino acid, you have to remember that you will add the pK values, that is the first pK1 and the pKr, and then divided by 2. So now if we go on to, supposing now we have to discuss the graph of a basic amino acid, and for an example I take an histidine as a basic amino acid, then we know that histidine has an alpha amino group, it has a alpha carboxylic group, and along with that it has a imidazole ring which has a proton which will dissociate at pK, that is at pH of 6.0, which we call as the pKr. So again for histidine we will have a graph which will have 3 plateaus in it, and for histidine the pH at which the species will exist as a zwitterion is pH 7.59, which is also known as the pi of that particular amino acid. So if we look into the structure of histidine, so what we find in structure of histidine is that histidine is a basic amino group, and since it has a basic amino acid, and since it is a basic amino acid, what we find is that it has 2 basic groups in it. One is the basic group of one is alpha amino group, and second basic group is present in the side chain. So if we know that when we are thinking of a species in a highly acidic medium, then all the groups will be protonated. So what we find in this case is that the COO minus group will also be protonated, and these group will be present as COOH group. Then we have a primary alpha amino group which is present as a ammonium ion, and then we have a amino group which is present in the side chain, but this is a secondary amino group here. And now when we increase the pH of the medium, what we find is that this is what you have to remember here again is that it is the COOH group which will undergo deprotonation first, and when it undergoes deprotonation first, we will get the second species, that is, and in this species what we observe is that this moiety has a negative charge on carboxylate group, it has a positive charge on the ammonium group, and NH does not have any charge on it. So that means the net charge, NH has a positive charge on it. So what we find is that in this case here the net charge is 1. So let us take back from the first structure. In first structure, since all the groups have to be protonated, COOH, carboxylate group is present at COH, then the amino group is present as NH3, and the second group is again present as NH. And then when we do the ionization, we increase the pH, what we find is it is the carboxylate group which will undergo the deionization, and we will get species 1. And what we find is when we talk of this species, it will have a charge of +1 because carboxylate group has a charge of -1, whereas the two basic groups, two nitrogens, have a charge of +1 each. So 2 - 1 will be +1. Next, again it will undergo deprotonation, and when it undergoes deprotonation, now the deprotonation will take place of the side chain. In this case, now the net charge is 0 because the two charged species present here are carboxylate group which has a minus charge and a ammonium group which has a positive charge. On increasing pH further, this will undergo deprotonation further, which will give us the last species. All this, how do we get +1, +2, +1, 0 and -1, and the different forms of histidine plus their graph I shall be discussing in detail in my next lecture. Thank you.